to tell us all about a song for compatibility and performance. So please welcome Ronan.
Thank you. Today I want to tell you the story of PyPy. I mean, story not in the sense of a chronological history, but more narrative of what PyPy is for, what it's about, and what we are trying to do. I'm a PyPy co-developer. I've been working on it for 6 years. And, let's talk about PyPy and start from the beginning. And in the beginning, there was Python. And I guess if we're all here, it's because we love Python. It's a very nice language. We can do pretty much everything with it. Except that the standard interpreter is not that fast. So soon as you need to do something that's computationally intensive, you can't really use Python anymore. So that's why people decided to create PyPy, which would be a fully compliant implementation of the Python language, but also a fast implementation that would allow all the Python programmers to do whatever they want without having to worry too much about performance. So, how did we implement the Python language? Since Python is a nice language, let's use Python to implement Python. Actually, it's not really Python. It's just Python-like. But still, using this RPython language allows us to implement all the various features of Python, and it allows us to keep up with the ever-increasing complexity of the interpreter and of the language. The other thing is that, you can use standard Python tools, so it's easy to test and debug. So I repeat, this is RPython, not Python, and the fact that we're implemented in RPython allows us to compile this code you see here into machine code that you will and into the PyPy executable. But at the same time, we have a whole toolchain that compiles RPython, and this toolchain adds more or less automatically the main feature of PyPy, which is the JIT, the just-in-time compiler. So what the JIT does is that when you are running your Python code and the interpreter detects that there is a hot loop somewhere, it will look at this at the code in this loop and optimize it and emit fast machine code, so that you get for this small part of the code basically the same performance as you would get in a compiled language. So with this technique, you can blend rather seamlessly the advantages of dynamic languages like Python and the performance of things like C, Java, whatever. And in Python, the JIT is not the only significant part for performance. We also have a specialized memory manager, or a GC, garbage collector, as it's known a bit reductively. So the problem is when you have a dynamic language, it allocates a lot of small objects all the time. Every single expression you have in your Python code creates a new temporary object that is often immediately used to do another operation and forgotten. So this pattern is not very good for a program implemented in C, like CPython is, where you have to use malloc and free, and in CPython you also need to update the reference count all the time. So every time you use an object, you need to say, hey, I'm using this object, and then if the function stops using that object, then it needs to say, hey, not using that object anymore, but maybe someone else is. So you need, that's why you have this reference count attached to every object in CPython, and that actually takes a lot of time. So in PyPy, the way the GC is tuned specifically for this pattern of creating a lot of small objects that have usually a short lifetime. Also, it doesn't need to keep track of this reference count all the time. It actually reclaims memory by just traversing the graph of all the objects that are still reachable from anywhere in your program. By the way, CPython also needs to do this traversal because of the problem of cycles, which is handled automatically in PyPy. We also have in PyPy, in the interpreter itself, a few optimizations that work with patterns you encounter in typical Python programs. So with the JIT and a bit of support from the interpreter, you get inlining of functions and methods automatically. So that means that, whenever you write a function call in your code, you don't have to worry about the performance penalty. So you don't have to do what some people tend to do when they want to optimize code for CPython, which is to inline all the things into one big function, because function calls are expensive in CPython. So in PyPy, it's basically free. Another important optimization is what's called instance maps. So every instance in PyPy is automatically turned into basically the equivalent of a struct at the C level. So the names of the attributes are shared between all the instances of the same class, and inside each instance you only store the actual value of the attributes. You can sort of do that in CPython if you use the dunder slots in 2.7 and until 3.5. I think starting from 3.6, there's somewhat similar optimization for objects. But anyway, since we have this optimization, you can just have objects which have attributes and not pay a penalty. for it. And another important optimization is what's called the list strategies. So lists, when you have a homogeneous list of, let's say, ints or floats, in PyPy, it will be stored as basically an array of machine-sized floats or ints, which is a lot more compact than storing objects and makes it a lot more efficient to access items in the list. So, with all that, well, what we get is faster Python. PyPy now supports fully Python 2.7 and 3.5 since last December. Not giving any numbers as to speed, because it completely depends on the kind of code you're writing. But it can be up to 100 times faster than what you would get in CPython. That means, well, different order of magnitude. You are in the same realm as compiled languages and not as what you traditionally expect from a dynamic language. Additionally, with cffi, which is convenient and simple way of interfacing with C code. And it also works on CPython. But on PyPy, it's extremely efficient because the JIT knows how to remove all the overhead of calling into C. And we've also developed VMProf, which is a statistical profiler that allows you to check how the JIT optimizes the code. So with all that, well, you can really have Python code that runs pretty much as fast as you could hope. And for me, I would say that speed is maybe not the speed for itself is not the main point of all this. I would rather say that because we can make Python faster, users can now use Python in a lot more circumstances and can use nicely factored, nicely structured, idiomatic Python code to do things that are performance intensive. So, well, I think that paints a compelling picture for Python. And but the thing is, it was more or less already like this 5 years ago, and there are not that many people using PyPy. So something must be missing, and well, that something is C extensions. A good deal of what makes Python a good language is the huge ecosystem we have. Things like numpy, pandas, LXML. Well, there are way too many to remember them all. So in PyPy, we do need to have a way to get these C extensions to work. And that way is called cpyext. So if you look at how a C extension is made, well, it's basically just some C code that gets compiled into a shared object. And well, what it does is it includes the Python headers at the top here, this python.h. And cpyext is just the subsystem in PyPy that creates a python.h that can be used by extensions. The issue and the difficulty for cpyext is that we have two very different worlds that we need to bridge. So you have the C world of the C extensions on one side and the PyPy world, and so the languages are different. The structures are different, but also the memory models are different. In C, you have pointers that that are specific locations in memory. In PyPy, the memory is managed and the object can move around because it's more efficient. C code doesn't expect a pointer to suddenly change. And there's other things like exceptions work completely differently. So, in cpyext, what we do is we have we have objects that live in both worlds. So the objects that come from the C world are linked to object from the PyPy world, and so it's we just add an additional field to every single object that the C extensions use, and the garbage collector knows how to handle this this link, and knows that if a PyPy object is referred by such a link, it needs to be kept around, and it knows how to emulate reference counts, etc. And it's a lot of well, a lot of interaction and to map these to a very different world. Well, the implementation of the function from the C API doesn't look that bad. We can still use RPython, and well, there's hundreds of functions like this to implement, but it's still doable. However, well, there's this decorator at the top, and this decorator hides a whole lot of magic that you have to perform every time you do a function call. So this every time you cross the boundary between the two worlds, you pay significant penalty in terms of speed. So, and it's also very easy to for developers to forget that there's a whole lot happening in this little decorator. So recently, so we've started less than a year ago, we've started optimizing CPython and trying to remove this overhead as much as we can. Well, it turns out it's quite possible to be more careful in how many times we cross the boundaries, and it's also possible to avoid crossing the boundary completely. So that means writing some parts in C. And with all that, we've made some we've had some encouraging results. So these are a bunch of micro benchmarks that by themselves don't mean that much. But so you can see in blue that's CPython as a reference. So everything is normalized to CPython. And in green, that's the situation before the optimizations. In red, it's after. So everything has become faster, and many things are now actually faster than on CPython. So, well, unfortunately, probably the most important micro benchmark in all this is this one, where we're still slower. But this gives us hope that we can have a fast cpyext. So, current status for C extensions, it's that we now support things like numpy, scipy, pandas, scikit-learn, LXML, all of Cython, everything that's, well, most things that are written in Cython. The only issue being that many libraries are not tested on PyPy, and if something is not tested, it's broken. But it's nowadays usually quite simple to just add PyPy support to any compiled library. Yeah, but for the most popular extensions, you can just pip install them on PyPy. Unfortunately, the wheels are not on PyPy, so you either need to compile the library yourself every time, or to use this repository of wheels. And to conclude, about what we are doing at the moment in PyPy. The next version of Python is obviously on the agenda, so we're working on 3.6. We hope, or well, we're quite convinced that we will be able to make cpyext a lot faster. We hope that more people from the community, maybe you here, will make sure that the libraries you care about are really compatible and tested on PyPy. And well, and if you're interested in PyPy, there will be a sprint on Wednesday, so come and talk to me afterwards. Thank you for listening.
Okay, thank you very much, Ronan. Okay, do we have any questions? I was going to say thank you very much for this, because this is very much out of my comfort zone. So.
Hi, I'm just wondering on like how much effort you think it is to get to 3.6 support and then 3.7, especially with ordered dictionaries.
So for 3.6, it's we're not that far. I guess. Well, it's not progressing very fast at the moment because nobody is funded to work on it. But it's I think just a few months of full-time work. So whether it will take just a few months or a year is a bit up in the air. But there aren't that many big issues to solve for 3.6. It's just a lot of small details.
Hi, I'm wondering, is the new typing stuff that's in 3.6 going to result in any speed-ups potentially?
Well, no, or at least not directly. The type hints are not, well, they're not precise enough to enable PyPy to do anything with it. And anyway, Python semantics say that these are only hints. So since we want to be fully compatible with Python, we just can't use them in any capacity.
Understood.
Okay, so we've got time for one more question here. There's one over here. Sorry.
Yes, so I was wondering, the RPython toolchain, Python 2.7 is going out of support at some point in the near future. I believe that's still a Python 2 code base. Is there any plan to migrate that?
No, we're not making plans on migrating the toolchain. Well, in PyPy, we are planning on supporting 2.7 indefinitely, so that will still allow us to run the toolchain. Maybe we should start thinking about migrating to Python 3, but it's a lot of work, and from our point of view, there's not much point to doing it.
Okay, so that's all the time for questions, but I'm sure Ronan will be around. Will he be around in the break afterwards for any further questions? So let's please thank Ronan again.